It's time to start the afternoon session. So the first speaker is Debabarata Ghorai from Hanyang University, and he will talk about momentum-dependent gap in holographic superconductors revisited. Please start.
Thank you, organizer, for giving me the opportunity to present my recent work here. And the reason for the revisiting this problem is that we want to try to find out the angular momentum number in the holographic superconductor models. So this work actually based on this archive and work done with the collaboration with Professor Sangjin Shin and Yeon Sik Chun. So, sorry. Yes, this is outline my talk. First, I try to describe the all holographic superconductor models in the literature, and from there I actually show the all the equation of motion for the all superconductor models can be written in some unified way, and from this we can show that there are some limitation. From this actually motivates us to revisit this problem again. And then I try to explain why the necessity of the vector field model in the first place to describe P-wave superconductor model, and also we calculate the angle dependent or momentum dependent gap structure in P-wave case. And then I try to explain if one can consider the angular dependent structure in the scalar field model, how this different wave state is generated, and that's the scalar field model. And then we compare actually P-wave state, the vector field model and the scalar field model, and then summarize our result. So start with the basic of the gauge gravity duality. This is the statement of the gauge gravity duality. And when we try to map with the quantities in the gravity side with the quantity in the gauge side, we actually follow the JKP prescription, where we actually written down the generating function of the QFT in terms of the on-cell action in the gravity side. And from there, we can define the source term, and also we can calculate the response from the generating function. And therefore, one can write down the dynamical bulk field in the gravity side in terms of the quantity in the boundary theory. So using this, one can establish this kind of gauge gravity dictionary, where the charge scalar field maps to the in the boundary condensation of boundary operator or something. And one can also map the gauge field with the charge density or the current of the boundary theory. And the black hole instability in the gravity side actually maps the QFT phase transition, and the Hawking temperature, one can map the QFT temperature. This is the associated with the critical temperature in the QFT side. So build up any holographic setup for the superconductor, we need some kind of second order phase transition in the gravity side. But it is not easy always try to find out the phase transition in the gravity side. So for second order phase transition, we need to kind of some solution black hole with scalar here to black hole without scalar here. There one can show this is kind of entropy is continuous. So this is kind of second order phase transition. This associated phase transition is the boundary theory, is one can explain the kind of phase transition between metal to superconductor phase transition. I will explain this one. So first we need to find out some black hole that has some scalar here below certain critical temperature. For that we need some scalar and we need some action for scalar hair formation, and this type of action first given by the Gubsar. And he actually saw that this using this action in the ADS space, one can show there is kind of scalar hair formation outside the black hole. So using this model, actually this Hartnell, Herzog, and Horowitz, they actually show some basic property of the high TC superconductor. Also calculate the energy gap and critical temperature ratio around 4, which is matches with the experimental value also. So this is on the great success. And here they actually map the matter field in the bulk side, map in the condensation operator of the boundary theory, or that is related to the order parameter of the system, delta kind of energy gap. So in this case, they actually did not consider angular dependency structure. So this is one can see that this is kind of S-wave holographic superconductor. Kind of this gap is isotropic kind of gap. But we know that this high TC superconductor, like the cuprate material, actually show the D-wave structure of gap. This is not kind of S-wave gap. So this is one limitation in this model, and I will try to explain other model also. This is the equation of motion for the scalar field model. And now, if one can try to build a model P-wave structure. For that, Gubsar in same year actually gives the non-abelian gauge model with this following answers. These answers actually give the only X, consider the X component part. So this is kind of breaks of the rotational symmetry in the XY plane. So this is the Lagrangian for a non-abelian gauge field. And later, 2-3 years later, then this equivalent vector model is coming out, and this is kind of given from this Lagrangian. And in this case, actually, this vector model, we consider only one component of the vector field, but this vector field only depends on the R. There is no angular dependency. So using this model, one can derive this equation of motion for the matter field. This is equivalent to the this equation actually equivalent when m equal to 0 case gives the non-abelian gauge field model also give the same equation. Now one can generalize this P-wave structure to D-wave structure by introducing or generalize this vector field model to kind of tensor field model. And this model actually given by this this paper. And in this model, they actually consider kind of this field only depends on the R, which breaks the rotational symmetry, also breaks the kind of also kind of flip under the pi/2 rotation in XY plane. And in this case, one can also calculate this matter field equation. So this takes something like this way. And if we write down this scalar field model, vector field model, and tensor field model for both cases, if we kind of map this following way, this is for S-wave model, this is kind of POM model, and this is kind of tensor field model. If we map this kind of relation, so we actually get the kind of unified equation of motion for the matter field sector. And in this case, we see that this S actually denote kind of the spin number of the field. So spin number of the field S equal to 0 actually give the S wave, S equal to 1 give the P wave case, and S equal to 2 actually give the D wave case. But there is this is depends on the spin number of the field. But actually, we know that from the condensed matter side, this S wave, P wave, and D wave superconductor actually depend on the orbital symmetry, kind of depend on the angular momentum number, not this kind of spin number of the field. So in BCS theory, from BCS theory, we already know this kind of gap structure. This is kind of for different case S wave and P wave and D wave case, different value of L actually give the kind of self-consistent equation of the gap equation. And we also know the cuprate or high TC superconductor actually show kind of dx square minus y square orbital symmetry. And that case, actually the gap related depends on the angle in the momentum space or depends on the momentum. So first time this kind of angle dependency structure try to describe in this following paper, but they actually show in the fermionics using this fermionic spectrum in the holographic model, instead of considering the angle dependence matter field. So in summary, one can say that in all the equation of motion actually does not consider the angle dependent structure of the matter field sector, and that's why they actually get the angle independent kind of gap structure. And another point one can argue that in spin number of the matter field in the holographic setup, is there any connection between the angular momentum number in the boundary theory? So we try to examine this thing. So for that, first we try to consider the vector field model to understand the necessity of the spin one field model for the P wave superconductor. So this is the vector field model Lagrangian, and from this we actually modified this, and such kind of it depends on R only, also depends on the coordinate in the boundary coordinate kind of XY coordinate dependency is there. So now we want to change this coordinate system XY to U theta coordinate system so that there is angle dependency appears. And this is then we saw that this actually matter field psi mu, actually there is two components, psi u and psi theta component, but they are not fully independent. They are related by this relation psi theta equal to minus u tan theta psi u. So from this, now one can derive this matter field equation. And in this matter field equation, it is the kind of partial derivative equation. And in this case, we see that there is a kind of extra piece appears in this term. So to solve this matter field equation, but to know this configuration of this matter field psi u equation, we first try to impose the vortex free condition. Vortex free condition kind of there is no vanishing psi matter field inside the sample kind of. That's why this we impose this vortex free condition. This is kind of plane perpendicular to plane. So this is the vortex free condition. And now we substitute the psi theta in terms of psi u. Then we actually get this kind of psi u equation. Now one can use the separation of the variable technique. Using the separation variable technique, we first try to calculate this capital RU. And in this case, we try to solve this capital RU kind of separation variables, capital U and capital theta dependence. And there we introduce the another separation constant called LP. This LP, when we solve this equation using the separation variable, we actually get this is the solution for this psi u, and this is the psi theta. Their capital psi are still unknown, but we know about the theta dependency structure in this configuration. So from this solution, one can show that this LP should be kind of integer because matter field should be one value in the 2 pi rotation. And from there, we can identify this LP kind of angular quantum number of in our holographic setup. And we try to now understand this solution using the normalization. We define kind of normalization of the psi x in the xy coordinate. So this is the formula for normalization. And if we put LP equal to 0 case, which represent the kind of SOF state, then we see that this normalization kind of logarithm divergent there. So we kind of exclude this state. So for LP equal to 1 case, this n kind of give the finite value. So this is the ground state for the PUFC, ground state for the vector field model. So from this analysis, we actually show this vector field model. In the case of the vector field model, LP equal to 1, actually PUF state actually give the ground state, not the SOF state. This is the one we can show this necessity of the vector field model. And this is the actual solution for LP equal to 1 case. This angle dependency structure automatically come in the solution. And so from this, we can say that the order parameter actually is for the spin one field, actually psi u, not this psi x, which is previously or originally in model, they actually claim the psi x kind of order parameter. So another way one can solve this problem, kind of one can consider the better field answers for the POF case in the following structure, psi x and psi u. And from there, one can define the order parameter kind of this way. So automatic the angle dependency structure already appears in the order parameter. Now we try to solve this equation, the radial part of the equation. This radial part means this capital psi r. So to solve this one, we first field expansion about this way, and we actually get this previous all the equation. The previous equation means all this equation similar to in the literature. So now we try to solve this equation by analytic technique using this asymptotic character of the fields. People already know about how to solve this. So I just recap how to do this analytic method in Sturm eigenvalue method. So in Sturm eigenvalue method, we first actually, to simplification, we define the Z coordinate, and then we transform all equation in the Z coordinate, and then try to solve the gauge field equation at t equal to Tc, and this t equal to Tc, this matter field should be vanished. So we can get the solution of the gauge field equation. There is, we define actually lambda, and from this critical temperature, actually we can written down in terms of Chi density and this lambda. Now one need to find out this lambda value. So to calculate this lambda value, actually we recast the equation near TC. So there we actually substitute the psi z kind of this structure where the CP actually unknown. If we give the using this term eigenvalue method and try to minimize this lambda value using this trial function fz following 1 minus lambda tilde z square, and this kind of trial function, then we actually get the critical temperature value. This is following way, and this also verified by verified using the kind of matrix eigenvalue method. And then we want to solve this, we want to know about this unknown CP. To do that, we actually need to solve full gauge field equation. Full gauge field equation means there is some nonlinear term also is there. So we try to solve this gauge field equation by perturbatively. So from this, this first part in the A0 T first part is the kind of solution for T equal to TC, and second part kind of is the perturbative term. If we solve this equation, we actually get this the normalization factor CP kind of this following structure. From there, actually, we see that this kind of matter field we at near TC, we actually get this TC matter field configuration, which is take this following from here. We already know all the quantity beta tilde is kind of numerical value, and also we know this FZ function. So we now try to this configuration of matter field into maps to the boundary and the order parameter. Since this matter field is depends on the moment, this matter field depends on u and theta, we can transfer into momentum space also, and there we can see that this depends on momentum. So from there we can define the momentum dependency gap structure, and this is the psi u actually momentum dependency gap structure takes this from. From there we can now using 2D Laplacian transformation, we actually get the momentum dependency structure of this gap function, and this is the gap function. Okay, this is the kind of only temperature dependence part. This IU is the angle dependency part. Since psi u is the order parameter, because psi theta is there is some coordinate singularity, so we consider this psi u is the order parameter. We actually treat this psi k u component is the kind of order parameter of the system, and we plot this psi k u in the this density plot in this is 3D figure. And this case we see that they are kind of p wave state kind of forming. So this gap structure actually give the p wave momentum dependent p wave gap. This is the for the vector field model. Now one can ask if we introduce the angle dependency structure in the scalar field model, how this wave state kind of structure is appears in this that case. That case actually when we say this u and theta dependency, when we consider this u and theta dependency in the matter field, that case we actually get the 2D Laplacian in the matter field equation, and 2D matter field 2D Laplacian. And now we try to solve this 2D Laplacian part separately. So to do that, this separation variable technique, this is kind of long equation, so I have not write down here. And this is the separation technique, and we actually try to solve this capital R u theta. And next part, we define this alpha is the kind of separation constant from this psi r to capital psi r to capital R u theta, and this L is the kind of separation constant between capital U and capital theta part. And from there, we actually get the kind of solution of capital R u theta, kind of this structure of from. And when we try to solve this equation, we need to some boundary condition to get the integration constant or something. So for this case, we actually consider the boundary condition like u coordinate as this u coordinate actually represent the coordinate of the sample. So this is kind of going to 0 to a sample size. And this L one can identify is a kind of angular quantum number of the scalar field model. And this will give you kind of Bessel function and e to the power I theta. And this case, suppose L equal to 0 case is the lowest state, it actually shows this kind of represent the S wave state of the ground, which is the ground state of the scalar field model. And the non-zero value of the L actually represent the P wave and D wave state of the system, but they are kind of excited state of the scalar field model. So this is kind of excited state, P and D wave. So if you plot this angle dependency part in the momentum space, so we actually get this kind of solution. This is depends on the kind of Bessel function, and this is kind of S equal to 0 case S wave state, P wave state, and this is kind of D wave state. So now one can ask that can we compare this P wave state from the scalar field model to P wave state from the vector field model? So do that. We actually compare these two states. So for the scalar field model, we know this P wave state actually takes the this kind of Bessel function, and the vector field model, since the psi u is the order parameter, the I u k theta actually represent the kind of P wave state of this model. So we now define some kind of ratio function between the imaginary part of this SOM model and the psi u, because the SOM model, they are also kind of two wave state kind of sine the e to the power I theta, this means kind of sine theta and cos theta. So there is two components. That's why we compare this imaginary part with these things. So this total ratio kind of give the independent of the angle. And if we plot this one, we so this certain value of the momentum range k, that actually give kind of constant value. So from this one can argue that P wave state in the scalar field model, P wave state in the vector field model kind of gives similar result up to certain k value, the momentum in momentum space. So now we try to actually compare this critical temperature of the both case, how this critical temperature actually relate the P wave state and P wave vector field model and the scalar field model. And there we actually calculate this one using Strum eigenvalue method or matrix eigenvalue method. In both case, we actually see the this case kind of critical temperature is higher for P wave model than S wave case. So now we try to find out why this is happening, because in the scalar field model, this mass is related to kind of delta into delta minus 3 mass square term, and but vector field model, this mass square term actually relate to the delta minus 1 into delta minus 2 term. So from there we can map this mass term of the the scalar field model and the vector field model, and we know the phase transition in the gravity side actually due to the there is kind of effective mass due to kind of change this phase transition due to the kind of effective mass. So because of this effective mass actually affect the phase transition, that's why this kind of critical temperature is higher in the P wave case. So this is our findings, and if we summarize, so first we in literature we know that there is no angle dependency matter field in the holographic setup. So we first try to develop the angle dependent matter field, and so that we can show about the angle dependency gap structure. And we also explain the necessity of the higher spin model to describe P wave state or D wave superconductivity in holographic setup, and also so that the corrected order parameter for the P wave superconductor. And then we also study the different wave state in the scalar field model, and then we qualitatively study that we compare the P wave state, and from there we can qualitatively say that D wave gap can be explained through the excited D wave state in the scalar field model also. And also we compare the critical temperature in the both case, but in this our model there is a limitation, because in this model we does not consider any fermionic field in the bulk side. So there is impossible to show kind of Fermi surface to show in the gas structure, and this can be appear this Fermi surface or the Fermi arc through the kind of fermion interaction with the tensorial field in the D wave case. That is the things, and thank you for listening.
Thank you very much for your talk. So are there questions or comments from online or offline? Then so I have a question.
Yes,
So,
yes, sure.
so you studied the angular dependence of
Yes,
holographic superconductor model with scalar and vector field. And also, can you consider higher spin field like spin 2 or spin 3 or spin 4?
yes, this spin 1 case, we actually in vector field model, we consider the spin 1 field vector model. And now we are actually trying to consider the tensor field model using the consider the spin 2 field model. So, our first motivation is to kind of how this spin number of the matter field in the holographic setup related to angular momentum number in the boundary theory. So there we actually show that if we try to explain kind of p wave structure, we need to consider the spin 1 field. Otherwise we actually show that in the ground state. The p wave state actually in scalar field model, this is kind of excited state, not the ground state. Only for spin 1 field, we show that this is kind of ground state, p wave state actually give the vector field model.
Yeah.
I have another question about your result. So when you calculate the ratio between pairing gap energy delta to the critical temperature TC,
yes, TC,
the number deviates substantially from standard BCS theory by more than factor of 2. In real solid state superconductors,
yes,
the deviation from PCS value comes through parameters which are material specific parameters. So what is the reason behind your result, which is different from PCS value?
which result, this TC value?
Delta over TC in
Ratio.
your case is like 4.
Yes, yes.
But that number in real materials is like 1.5.
No, actually, this is for weakly coupled superconductor. This model actually describes the high TC superconductor, strongly coupled superconductor like Q-plate. That case actually we see this ratio kind of 3.78 or something. This is a kind of around 2 times, not exact 2 times in the case of the high TC superconductor. So this model,
so my question is,
holographic data, it is.
My question is, for your number like 4, what is the physics underlying this number? In your equation, what is the source for this number?
Okay, so in equations, number is kind of this actually delta beta tilde value actually give this number kind of beta tilde, because this kind this size actually maps to the boundary of a kind of maps with the delta. So this beta tilde actually give the number.
I understand, but as I said, your addition of this value means some material specific parameters. Yeah, I guess that maybe different material have a different coupling. Therefore, I guess that here, also, it seems that this number is clearly seems to be universal. Is there any material specific side of this number? Right. So that depends on delta tilde. So Diva.
Yes.
So that ratio, what is the input parameter which determine that ratio?
Input parameter actually we calculate this kind of CP, this is normalization constant. This input parameter kind of this lambda in this case. there is no boundary input parameter in this case. All in the a kind of calculate in the side of the gravity side. So the input parameter kind of the solution actually give, when we calculate this is kind of give the normalization constant of this value.
But I think that the CP is not fully determined, right?
CP for the P-wave model is fully determined, but for the scalar field model, this CP actually fully not determined. Vector field
No,
model,
I guess so. So the Professor Che's question is what is the model dependent feature? I mean, which can be different from one model to the other model.
other model mean this S-wave and P-wave case. No.
So you say that there isn't any dependence on the coupling or density or
No, there is
nothing.
no dependency. Coupling.
So seems that this is very universal.
Yes, kind of universal.
So, is there another short question? No? Then let's thank the speaker again.